a strong, we can have a strong reading of this, which means that exactly the shape or the position of the body is involved in the learning or the problem solving. But typically, typically we take a weaker reading. Okay. So typically we take a weaker reading of this, which is that when you move the body into a particular way, in a particular arrangement, then that gives us a new representation, and that representation allows us to learn concepts and so on. So for instance, when we hold something, or when we do something, or when we keep our hands in a particular way, then that representation becomes a part of the representation of the concept. The second thing is that cognition is embedded in the context and the experiences that we have. The third is that it's extended to the outer world, which means that the tools that we use, the environment that we interact with, all of this becomes coupled with us, and our thinking extends to those objects as well. And the fourth thing, the enactive idea, is that cognitive processes are based on action. So it's based on movement, and we can therefore also use them to simulate, to predict what is happening in the world, right? And so what the view of sense making and learning that we take is that objects and the environment become a part of or extension of our minds, and our minds move in the way of our surroundings, and they are able to simulate and predict the surroundings. So there are two processes by which we are making sense: interaction and simulation. This is what theory suggests to us might be the processes by which science learning is happening. What I propose that we do is we try to formally understand these processes systematically, and then redesign learning environments that can support these kinds of 4E cognitive processes. So to do this, coming back to an idea that I talked about yesterday, we first need to understand sense-making and learning mechanisms, and then we design novel environments which will enable us to further understand these sense-making and learning processes in this reciprocal process of theory building and design principle building. So before we actually go into how we are going to do this, I want to talk about how the work that I have done has enabled me to develop a kind of approach which we can use to study this learning more systematically. So there are two approaches, and I'm going to talk about how I propose to combine these in order to study learning better. So the first approach is about actually designing novel learning environments and using them to do further sense making and learning. And we go back to a context which we had yesterday, which was the algorithm design. There are these students working, there are these students who have to solve the problem of connecting all the minds with the minimum cost, right? And this is important, just to reiterate, because algorithm design is an important part of computational thinking, which is now being recognized as being very important, not just in terms of coding and programming, but in terms of a way of thinking and problem solving. So the question that we were going for, that we were addressing in this work, was how can we support students when they are learning algorithm design? And here's what we did to go about systematically exploring this. So just to remind you of the activity that we were doing yesterday, this is the QT robot. These are the two children working on their respective screens with a barrier, and they're collaborating, right? So we redesigned the learning of this concept by doing multimodal quantitative analysis of the differences between the learning processes of those who learned and those who did not learn within this learning environment. Just a quick, so to start with, we had to have some activity design. And so we use literature to guide us on what are the principles for this activity design. We deliberately made it open-ended because we want students to participate in any way that they like, because we don't know yet what is the right way to do this. So we just give them a lot of affordances on this interface, and so they can interact in any way that they like. We scripted the collaboration, and that is for purposes because to allow even participation and to make sure that they talk to each other, they share information, and because we know that conversation during collaboration is useful. And the robot is just mediating by guiding them from one activity to the next. So it's, as you can see, it's a pretty bare bones design. We don't have many supports inbuilt over there. A quick reminder of the two views. We have one partner who sees what's called as the abstract view, and one who sees this concrete figurative view, and then they share the information. So what was the research question we had over here? The research question was, how do novices learn from this open-ended collaborative environment? And specifically, what we wanted to study was that what are the actions, what are the actions of learning and what are the processes of learning? And these two are going to help us answer the question of how we can then redesign this. So what we did was we collected multimodal data. By multimodal data, we mean we collected the logs of all the actions, everything that people were doing. We collected their eye gaze, and we collected some measures of their affect and their speech. And all of this was what is called done through cheap data collection, the goal being that it should be doable with minimal resources in a classroom. So we used a video camera and tried to extract as much information from that as possible. So the speech, the affect, and the eye gaze data was extracted just from the participants' video. Okay, so affect is the emotional state. So this is measured by using two metrics, which is the arousal and the valence. So arousal is like the level of excitement, and the valence is the disposition. So is it happy, sad, and put together, this can say a little bit about frustration. That was because there was one hypothesis related to frustration and how it affects learning in failure-driven environments.
But how do you extract this from the video?
Okay, so it's a long process. So there are these action units on the face. So the software which is there, it can extract those software units, and then the face units, the facial muscles basically, and then the activation of each of these. There's a level of activation of each of these that relates to the valence and the arousal. So
maybe you should just repeat the question because GM says, please repeat the question.
Okay. Yeah. So the question was one, what is affect, and how do you measure affect? So how we measure affect is that we have on the when we record the video. So we zoom in on the students' faces, and there's already research and there's validated methods which say that there are these 17 action units on the face, essentially 17 muscles on the face, and the level of activation of each of these is related to the valence and the arousal. So this is done using very standard pipelines. So you can just extract the activation of each of these, and then what the algorithm outputs is a number, which is what is the level of arousal and what is the level of valence of this particular face. So
does the software give you this output, or you have to do this?
The software, so there's something called OpenFace, which is an open source library which is available, and so you can just use it with Python and it can give it. So the question was, do you have to do it, or does the software give you this? So there is a software called OpenFace, which just gives this as an output. Right. The similar way, there's another library which can extract the eye gaze and say whether the eye was looking left, right, front, sideways and things like that. And then for speech, we did not use any quality of speech measures, but again, we used cheaper measures, which have been already shown in collaborative learning to be representative of the quality of learning, which is the amount of speech and the amount of overlap of speech between learners. So we use these very easy measures. In terms of actions, this is the list of actions that we used. So the number of times that people added an edge, the number of times that people deleted an edge, the ratio of these, the total number of actions, the number of times that people looked at the history. And these last four measures are sort of derived measures, but they are interesting because they portray a certain kind of evaluative action, which shows this, that one person, what this means is that a person deletes and then immediately adds back, or the person adds and then immediately deletes back. And these kind of complex actions, they signify that they were doing some meaningful interaction, which means that they were thinking about that and so on, thinking about their actions. So we calculated these as well. And the redundant edges was just the number of times people had extra edges on their map, which is a metric because it's a metric of how well their solution was working, because ideally there should not be any extra connections in the map. And then talking about the video and the audio features, which I already just described about, we look at positive valence, negative valence, which means what is the average value of the positive disposition, what's the average value of the negative disposition. And then the arousal, which talks about how excited the person was, and then smile, the number of times the person was smiling, which was not very useful, and then gaze measures, and then speech measures. Within speech, one important, two other features which we use for pauses, and pauses because they signify that there's something which is happening. Either there's some action happening or there is some moment of no action and thinking, and so that signifies that something else would be happening. So our analysis perspective for this was an action-based perspective. We believe our theoretical perspective tells us that the actions that are done during the algorithm design process feed back into the thinking of the person, and the thinking feeds back to the action. So there is this bidirectional coupling happening. So that the way that applies to our case is that we look at the people's learning gain and their performance, and we relate that to all of the multimodal actions that we just talked about. And the idea is, so the analysis idea is,
Question.
yeah, yes.
This is from Ravi.
This is from Ravi Subramanian asking, did you use any interpretive measures to analyze speech? For example, asking a question, responding, sharing information, disagreeing, etc.
Yeah, so not in this one.
I know the question was audible to the Zoom audience. If you use the mic for the question, is this okay, or does she need to repeat it? Can somebody use this say?
We can hear the question.
Okay, go ahead.
Yeah. So did we use any interpretive measures? For this analysis, no. And this is a feature of this analysis approach, where we begin with features that are easily countable and do not require any interpretations yet. And the goal is, I'm just going to talk about the goal. We did interpretive analysis later. So the interpretive qualitative analysis of the nature of the talk comes later on, because it gives something which I will just, this hierarchical approach brings something which I will just talk about. So what we want now is, we want action profiles of learners and non-learners. So simply put, we want to know among all of these multimodal actions, what was the features of the actions of learners, what was the feature of the actions of non-learners, and what was different between them essentially. So what we try to do is, every team has a set of actions. And we try to identify which of these sets are close to each other. And this is done using an approach called, done using an approach called as clustering, which is basically a data mining approach, which tries to find when certain sets of data are similar to each other and using some similarity metric. In our case, we assume that all of these actions form a point in an n-dimensional space. And then we use the distance between these points, Euclidean distance, as a measure of similarity. So you can see over here, essentially what we are doing is that there's this space and it has all of these features, and we are trying to partition the space into parts. You have a question?
Yeah, I'm not sure how this similarity came in. I think I missed your explanation of similarity.
Okay, so we want to group sets of actions or groups of actions which are somehow similar to each other, because we want to know, or were there any similarities between, some kind of people?
Like adding a line or deleting
Yes,
a line. Those
yes.
are your actions.
No, so the whole set which we had, this long thing, all of these actions together, there were 25 actions in all. This is considered one point, one data point. That's the multimodal part of it. So all of these actions are considered together in this 25-dimensional space. And then we try to find which of these points are essentially close to each other in the space. So over here. So essentially, which of these points are actually here. So which of these points are close to each other and which are far from each other. So that similarity metric can be anything depending on the nature of the data. Here, since we are using real numbers, we are using a Euclidean distance metric. Okay? Okay. So we are grouping these people on the basis of their actions, and we are able to find out that there are what are the profiles of these learners essentially. So there is one group. So essentially in this space, there are in this space, there are some points which are collected over here. There are some which are collected over here. There are some which are collected over here, because all of these are similar to each other. So they are close to each other. And there are some metrics by which we can compare that. So these are close to each other. And at the same time, they are different from the others. So then we look at these people who are grouped together, and we see what was their learning performance, what was their learning and what was their performance. And what we find is that in the three groups, which we named expressive explorers, calm tinkerers, and silent wanderers, which I will just explain in the next slide, there is significant differences in the learning between these three groups, not between all three groups, between the third group and the first two groups. So what this tells us is that there are two sets of actions which signify high learning, and there is one set of actions which signify no learning. So this is now able to tell us that we can differentiate people entirely on the basis of their actions. So using this, what we have now been able to do is to separate people on the basis of their actions, and we have found that they also differ in terms of their learning. So this method,
the three categories are made independent of those values, right?
Sorry?
The first three categories,
the names. Yeah.
How are the clusters made in the first place?
The clusters are made using the action metrics. But then we see what are the corresponding learning metrics of this group. And then we find that there are differences between the learning metrics of these groups. So let me just go back. So the clusters, so if you just imagine that these actions are all of these points in the space. So we separate this space into parts and we group the points which are close to each other, all of these actions which are close to each other. And then we see, okay, this is team one, this is team X1, X2, X3, this is X4, X5, X6, This is X7, X8, X9. Now we see, okay, but what was the learning of the first group, X1 to X3? What was the learning of the second group, X4 to X6? What was the learning of the third group, X7 to X9? And what we find is that this is different. Okay. So what this is now gives us, yes.
Question from Ravi: why would you use an Euclidean distance rather than say a taxi cab metric for clustering?
I am not. What is the taxi cab metric? Okay. I don't know about the taxi cab metric, but I think in this case, the
taxi
Euclidean
cab.
distance.
Taxi cab metric is just adding the differences in distance along particular dimensions.
Okay, because okay, so here adding the difference.
You go in straight lines. Like if you have a XY grid, you don't take the diagonal, but you go, just horizontal, vertical, that kind of metric.
Okay, yeah, but Euclidean distance is a more common metric which is used, and in a real dimensional space, won't it make more sense to use the Euclidean distance? Because we have all real numbers which are normalized between a 0-1 scale.
It would, but this is a 25-dimensional abstract space. So anyway,
Yeah,
I mean, it's not important. It's okay. I thought you might have some idea. I was just curious. It's not a, yeah. Okay, thanks.
Okay.
Yeah, it's the L2 versus L1 distance, right?
Can you just please repeat that word that one? Anvesh, do you have a question?
No, I was just saying that it is the L2 versus L1 distance. The two things. The Euclidean thing is L2 and this is L1. So it, yeah. Anyway, I think she should continue.
Okay. Subra has a question of: can you repeat the actions? Whatever actions they were doing.
You want me to show the actions again?
No, Subra, what was the question? Can you just unmute and ask?
Yeah, I was just asking what are the actions actually? Can you just say, are they? You had this diagram. Just keep it on here.
Yeah, you can take a look.
Yeah, thanks.
Is that okay? Shall I move on?
Yes.
Okay. So what we have now is we have 3 sets of learners and 2 types who had learning gains and 1 who did not. And what we found is that now that we compared essentially the action metrics of these 3 groups using standard statistical approaches, doing like Kruskal-Wallis tests. And then we identified what are the differences between these 3. So now we want to know what are the actions which are productive for learning. We know that there are these 3 sets of learners. They have different learning metrics and they are also different in terms of actions. So in what way are they different in terms of the actions? So what we found is that the first thing is that in terms of speech, in terms of all metrics of speech and speech overlap and so on, the groups who learned spoke more than the groups who did not learn. So hence the name silent wanderers for them. And so these peaks, if you're wondering, these are the silence peaks actually. Silence and long pauses. So these were people who were having either keeping quiet a lot or they were having long pauses. And so that was not very productive for their learning. And this is already a known result from collaborative learning. We just re-established that. But what was interesting was that there were 2 approaches to learning, or there were 2 kinds of actions which people were doing, which we have not seen before, right? And that is the expressive explorers have they have very high actions, but they have very low number of removal actions and T1, T2 type actions. Now, T1, T2 type actions means that I added and then my partner removed, or I added and I removed. So this signifies this sort of a bit rapid evaluation and removing type of approach. Whereas the other approach was that they were looking more at their history, and they were looking at their history, and then they were doing a lot of addition actions, making the map, seeing whether it was correct or not, then looking at their history again. So this signifies a sort of a global approach or a global action strategy versus a more local action strategy. So you cannot see the history numbers over here because we have only plotted the ones which had the top 10 most differences, because there were 25 of them, but the history was also significantly different. The access to the history was also significantly different between the two learning groups. And because one of the groups was having this more global action strategy, we called them explorers. And because the other group had a more rapid changing strategy, we called them tinkerers. And finally, what we found was that the non-learners had low actions, but that was not the problem. Even the tinkerers had low number of total actions, which was not a problem, which is not a problem. But they had no focused exploration strategy, which means they were not doing enough evaluative actions, either correcting themselves or looking at the history and so on. So that was one of the reasons why their work was sort of not good. Is there a question?
Yes, actually on the earlier slide, before you go ahead perhaps, what is the underlying assumption on the statistical distribution of the variates or actions? Because I can see that some of the actions are discrete and some are continuous.
No, they are all continuous.
Okay, the answer is they're all continuous.
Yeah. So, okay, so now we have these profiles of learners. We have two kinds of learners: expressive explorers and calm tinkerers.
Sorry to interrupt, Aditi. They're all counts. Am I correct? They're just counts. All of them are integers, right? I mean, action counts.
They're counts. They are counts. But no, the speech values and so on are just real numbers, because they are, how much time were they speaking, how much time were they silent, okay. What was the
it is
values
in terms
and
of
all that. And then
times,
and then everything was normalized to be between 0 and 1 to do the clustering. So after that, everything is worked in the mapped space.
Sure. And I mean, I don't know if I might have missed this. Did you mention after clustering, what were the variables which were obtained, the reduced variables, or I don't know if you've discussed that already. So
No, I didn't talk about that. I didn't talk about that, and I don't have the data handy with me right now. You mean, sure. Yeah, I don't have the data handy with me right now. But these were the variables. What I'm talking about here are the variables which showed statistically significant difference between the clusters.
Okay. Okay. Yeah. Thanks.
Okay. So now that we know this approach tells us who are learners, who are non-learners. We know what are the action profiles of these learners. Now, what we want to know is about their process of learning. So how do these actions that they're doing, how do they change over time? And how does this evolution differ for learners and non-learners? Okay, so here what we assume is that now earlier we had that all of those actions which were aggregated across the whole interaction. Now what we did is that we split that up for every 10 seconds of activity. So now we know what people are doing in every 10 seconds. Then we assume that these actions are representative of a hidden state of learning. So it's some hidden process of learning that's happening underneath that we don't know and that we want to find out. And these behaviors are just the representation of that state. So what we do in this case is we apply what is called as hidden Markov modeling, which does exactly this, which assumes that there is a hidden process which we don't know, but then there are some observations over here. What you see are observations which can be seen. Now, our goal is to find out what is this process which is there at the back, so that we know how it changed over time.
So mathematically, a process is a way of connecting these various points in your n-dimensional space.
Yes, exactly. Yeah, we want to connect this
So
across time.
Sequence
Yes, exactly.
In your n-dimensional
Yes,
space.
exactly. Yeah, that's the idea. That's the idea. We want to find how it moves across time.
This you do in Python, or how do you do this?
So yeah, there is to build the Markov model, there are some packages in Python. Yeah, it was done in Python. It was done by a student who was working with me, but yeah, he used a package in Python. So yeah, so now we build a model of what was happening behind, and what we assume is that, I mean, when we are looking for these states at the back, right, there can be any number of states, of course, because we don't know the nature of this, but we assume on the basis of the data, on the basis of some exploration of the data, that there were 3 states at the back which were giving rise to this observation. And the assumption was based on the fact, on some preliminary analysis with the clustering and so on. So we assume that there are 3 states, and then we run this algorithm, and the algorithm comes up with the features of each of these 3 states, right? And what it comes up with is what are the nature of the actions in each of these states. So I'll give you an example of what happens. So for the expressive explorers, there are the 3 states, right? And one of the states is the state in which the actions, the people are speaking less, they are doing less actions, and they are asking more questions. This is a state which mostly occurs early in the activity. So we interpret that this is like a state which happens in the beginning when students start. They are a bit confused. So they start from a state of non-productivity. Now, the other state is a state in which they are doing more actions. They are speaking a lot more. They are doing more actions, but they are doing a lot more of the local actions, which I was talking about. So rapid additions and deletions and so on. And then the third state is one in which, again, they are speaking a lot, but they are doing more global actions. So they are doing more actions of the type they add, they build a solution, they look at their history, and then they go on, right? So this together gives us a model of the learning process of the expressive explorers. How does this give us a model? The transition between the different states are given by probabilities. So these arrow marks denote the probabilities of transitioning from one state to another. And the higher the probability, it's the more green rather the arrow is. So what we know, what this is telling us is that when the people are in the state of non-productivity, right, they stay there for a while, but then there's a very high probability that they will transition to another state of global problem solving. And a very high, almost equal probability that they will go to another productive state of local problem solving. And they also go back and forth between these states. Now, why is this important? Because this tells us that it's not like people are behaving in the same way throughout the problem solving activity. They start in a confused state, but then they go to both of these problem solving states with almost equal probabilities, and it seems that they are switching between these two states. Probabilistically, they are switching between these two states. So we cannot infer just by looking at a person, or if the robot is looking at a team for one instant, they cannot conclude anything about that, because their behaviors are switching across the activity. And this is important because this allows us to intervene in a more thoughtful manner now. We found similar results with the other learning group, except it's just a little bit in terms of the time, whether, I mean, it's more probable that one group does a local strategy at the beginning and a global strategy at the end, whereas it's reversed for the other group. But essentially, the takeaway is that both of them do both of these strategies, and they have a sort of an aha moment. So what these high probabilities tell us is that, sorry, what these low backward probabilities tell us is that there is like a transition. Once they go into that productive state, there's a very low chance that they will come back. So there is some sort of a transition in productivity, right? And there's a transition in the actions. And that is important, because now we know that there is some moment at which something happened, at which we can zoom in and try and identify what was the exact processes that were happening. Whereas coming to the third group of learners, what we found was that, yes, they also had this non-productivity state, but they did not have very high probabilities. So you see that this is light green, and the transition to the other state is also not very high. So they have very low probabilities of going to these other states. So in some sense, we think about it as a more gentle transition to the productive state, and a transition which comes very late. So what happens is, in some ways, we can think about it as maybe they didn't have enough time, they took more, they needed more time to understand the problem, and so on. So if we can see here, this state from which the chance of going back to the state of non-productivity is very low, this happens exactly at almost the end of the activity. So that's why these people were not successful. So what this tells us is that, okay, we need to intervene with these people earlier, because we cannot allow them to go into this light green state, which is it's a sort of an unstable state. From here, they can very easily fall back to the state of non-productivity. So if we find them over here, we need to intervene and make them move to another state. So yeah, so we did all of this analysis. What did we get? Why did we use all of these complicated methods? Why did we use all of this code? Because this tells us something that the human eye could not have seen. It allowed us to separate these behaviors into groups which we could not have seen otherwise, right? And what we found was that there are two approaches to learning, but both of these approaches have both generative actions and evaluative actions. But evaluative actions are necessary. Without the evaluative actions, they are in the the silent wanderers group of of learners. And then it tells us that all learners start in a state of low action and speech. So it's okay. They will take some time to get used to the activity. But what the important thing is that one of the features of people who learn is that they switch into a productive mode. And by productive, I mean, I'm calling it an aha moment, but we don't know exactly what happened. But for definitely what we know is that they switched into a mode in which they were speaking more and acting more. And that is productive. And the silent wanderers were more sort of going very gently into this mode where they were talking more and acting more, and they could anytime, sort of fall back into the unproductive mode as well. So this is nice because now this allows us to define very pointed interventions where we take this data that we collect in real time. There is an algorithm at the back which is analyzing it, and then which can look at the data, map it back to these findings, and then give some interventions. Yes.
So how much of these characterizations are you ascribing to the task, and how much of you are ascribing it to the students? So are you saying that, okay, silent wanderers, is it a characterization of the students, or it's a characterization of the activity, or a mix of both?
I'm not, this is not like, this is not a judgment on them as learners. It's just a characterization of their activity within that learning environment. That's all. So
what general implications for instruction or education can you draw? Like how can this be utilized in?
Okay, so generally this is true that when there is collaborative learning happening, speech and lack of speech is a problem. So speech is the primary mechanism by which collaborative learning happens. The wanderers part is a little bit, why we call them wanderers is because they had low evaluative actions as well. And evaluative actions show that you have some plan or focus or something about, what you want to do, and, you're doing an action, you're getting some information back from it, you're feeding back. So that feedback loop was not happening. That is the feature of their interaction. So low speech and low evaluation. That is the reason why they are being called silent wanderers.
So from this, like, how do you feed this back into like the redesign of the activity?
Yeah.
Like, how does that happen?
Yeah. So what happens is there is a levels of intervention, and the top level is speech. So it's constantly monitoring speech, and there's a cutoff, and this is all this is heuristics, right? Because we can't know for sure. But then looking at the values that we got, we set some cutoffs for the how much speech is productive, and then it's being monitored for some time, right? And because the initial phase is anyway low speech. After some time, then if it's after a particular cutoff, I think it's like maybe 2 or 3 minutes, because the activity is only 25 minutes long, so 5 minutes. Then you see if the speech is still not at the right level, then the robot intervenes and says maybe you two should talk to each other. So these are just gentle nudges, because we can't force the children to talk, but this is like a nudge. So maybe you two should talk to each other. Maybe you should tell each other what is on your screen. Maybe you should share what you are thinking about. Maybe you should tell your partner what you want to do next. So things like these are repeated by the robot.
So the purpose is like, okay, to program the robot to give better intervention.
Yeah. And no, but see, just in our case, it was a robot, but that's secondary. This exact information can be used by a teacher, right? If a teacher is watching, right? Okay, I don't need an AI to see it. If a teacher is watching, a teacher sees, and a teacher knows this very well. In terms of speech, at least a teacher knows this, right? A teacher knows this, that if they are speaking less, you go and intervene and tell them to talk to each other, right? That the teacher knows. What is new is this thing of evaluative actions, which a teacher also may not know. So if we can, for example, tell a teacher, look, this team is doing low evaluative actions. They're not looking at their solutions. They are not looking at what they just added and deleting it. Then the teacher can go and intervene. and say that maybe you should, did you look at your previous solution? Do you think that what your partner has done is correct, and so on. So that's the goal, creating productive interventions. And in makerspaces, I see it more as maybe a teacher or a facilitator. I don't see it as a robot doing these kinds of things.
So nothing like about the redesign, the feedback into the redesign of the activity.
Yeah.
Any implications for that?
Yeah, so that is what I said. For the activity was redesigned on the basis of this. So there was a new protocol sort of built into the robot, which is listening to everything, and then it's listening to the robot. That's the first intervention. The second intervention is for the kind of evaluative actions, and then it's checking that. And then there's also one intervention for affect, but that is a secondary hypothesis. So if we observe that there is more of frustration, then sometimes we give them some encouragement. Yeah, so coming to the, I'll briefly talk about it because Ravi had the question about interpretive features. So interpretive features are, because the project that this is going on, the goal is, it's an educational robotics and the goal is an AI. Interpretive features are hard to automatically pick up, in runtime. So that's why we didn't do that analysis initially. We didn't include any interpretive features. But there is a follow-up analysis that we did, which I'm not reporting because it's very recent. But what we did actually is, now we zoomed into these episodes. We zoomed into particular episodes of productivity. And then we tried to interpret what was the nature of the speech at those times and what was different between the nature of the speech in the learning groups and in the non-learning groups. And one of the main things that we found was that in the learning groups, there was a lot of coherence between, of course, one utterance to the next, and there was repeated alignment on the goal. So they were constantly asking questions and agreeing on the goal. Oh, this is the goal. Yeah, this is the goal. Okay, and so they're agreeing on the goal and making sure that they're all on the same page. But in the non-learners group, what was happening was that there was lack of coherence, often from one utterance to the next, often even until the end of the activity. Sometimes they were not clear among themselves what was the goal and so on. So
okay, GN has a question saying, what I read in the implication of findings appears still as observations rather than implications. And can you clarify?
Okay. Yeah, so right. Okay, so the implications are essentially, this is like a summary. The implications are essentially the pedagogical interventions that I just described to Mashood. That the implications are that it directly feeds into the redesign of the intervention algorithm for the robots in terms of a hierarchical intervention algorithm. So since speech is the first level of differentiation, first listen to speech. Since the second level of differentiation is the reflective actions, then look for reflective actions. The third point being, since there is an aspect of time and how people's behavior changes across time, allow some time to pass and then change the intervention according to time. So these are the features which were then built into the next level of intervention. Okay, any other questions? Okay. So, okay, this is actually approach 2. So
I have a question. Can I ask?
Yes.
Yeah.
Sure. Sure.
So can you just go back to the previous slide? It's useful to. Yeah, thanks. So, I mean, it's interesting that from a behavior analysis, purely of behavior, you come to certain categories, which are interpretive categories. In the sense, what I mean is expressive explorers, calm tinkerers. I mean, these are very meaning saturated categories.
Yes.
So my question is, of course, I think they refer to processes of learning rather than learners per se or task per se, and maybe they can be generalizable that way. But my question is that, did you see, when you did the interpretive analysis, did you see support for these categories? And also process categories like switches which happened. You said that they switched from one mode to another. So did the qualitative analysis reflect and support those categories?
So I'm afraid I can't comment on that because the process, the interpretive analysis was done with small episodes where small episodes that were centered around certain moments of importance in the action. So what we chose was the moment at which students choose to submit the solution, simply because it was a long interaction, and because of time restrictions at this stage, I mean, a full analysis can be done, which is what I'll report in next. But in this one, we didn't do it. We chose to focus on moments where people had just submitted, and then we chose to see what was happening over there. So on the basis of that, I can't generalize whether we saw this across the entire activity or not. So,
thanks.
Okay, there's a question from Sanjay Chandrasekhar who's asking, are these states also thought of from a teacher training perspective?
Can Sanjay elaborate the question?
Sanjay, can you unmute and ask? Can you elaborate the question? Okay, Sanjay says, that is, apart from redesigning the robot's responses, are these moved to teacher training programs?
Yeah, they could be, and that is what I was talking about to Mashood, that for this project, of course, it was a robot, but the way I see it, these findings can also be used by teachers to support students better. So if teachers are told about these categories, and these are very simple observations that they need to make, even though initially we started with a large set, what we have finally come to are very simple actions. The first being speech, and whether groups are speaking or not, it's easy, relatively easy for a teacher to see to just observe. And then the second thing which they have to see is whether they are doing these evaluative actions. So these kind of pointers, if they are given to teachers, then definitely, yes, they can use them to, it can be part of a teacher training program. Suppose if we envisioned one where we were telling teachers, how should you support students when they are working on this activity in a class, then these were the things, these were the guidelines that I would give them, that this is what you should be observing for, and this is how you could potentially intervene.
Okay, Ravi, you have your hand up. Do you have another question? If not, Gian has a question on the chat. So, okay. So maybe Nagarjun's question is another clarification I would like. The analysis is largely behavioristic. In other words, inactive.
Yes.
Where is the embodied cognitive model, or am I misunderstanding something?
I am taking, for this analysis, I am taking the enactive perspective of the 4E cognition model. So this analysis is purely based on the enactivist perspective. So it's based on the perspective that actions and doing and interacting with the environment leads to cognition. That was what I mentioned up front.
Okay. Good.
Okay. So what we did, what one approach now to analyze these complex problem-solving environments is to have all of this data and to use quantitative methods to kind of do it in a way that reduces some of the initial effort of humans. But there are a lot of things which this doesn't give us, who as just now, I'm sorry, I didn't get the name of the person who asked the question, but can you have the interpretation across the entire process? We can't do that with this kind of data, because that kind of interpretation requires a human researcher's eye to look at the entire process and kind of try and understand what's going on over here. So there's another approach which we've also used in work, which is first understanding the sense-making and learning mechanisms, and then using that to systematically design novel learning environments. So we come back to the case of engineering estimation. Here today I've presenting a different problem just for fun. Yesterday, it was about the power of a car. Today, it's about the power of a plane. But very similar ideas. So essentially, you have to determine a physical quantity within a physical system without having complete information, without having information about what it's going to, where it's going to work, so on, because it helps you to do a lot of things like plan projects and so on. Now, the issue when we started with this project was that the pedagogy of estimation was unclear, right? Students have difficulties, but no one knows how to help them. Estimation is not even a part of formal engineering curricula. There are no teaching learning strategies, and the estimation process is not characterized properly in detail. So that was our motivation. We said we would start by first understanding what is a productive estimation process. So here we went through a series of 5 cycles where we first studied experts, then we studied novices. Then we also did smaller studies to try and slowly build up an intervention, which led to the learning environment that I already showed a demo of yesterday. But here I want to focus on how we studied experts and novices using a very interpretive approach to try and understand what it is that they do and how is that differ. So how we go about this over here is we first, of course, we do a literature, we develop some conjectures about what are the expert and novice processes and what could be the underlying cognitive mechanisms. And here we look at relevant literatures in ill-structured problem solving and model-based reasoning, because there is some research which suggests that estimation involves making models, but we don't know the nature of these models, what, and so on. So we're just looking at literature. And this gives us some conjectures, right? That the expert process of estimation has to do something with model-based reasoning. And given our embodied and enactive approach, we say, given our enactive approach, we say that this has to do with mental simulation and the extended approach where external representations are used. And mental simulation is based on the motor system and external representations are incorporated. Whereas novices would be following an entirely equation-focused approach, and their first thing will be, let me find an equation and so on. So to do this, we ask the question, what is the expert estimation process? What are the cognitive processes that are there? So the way we did this was that we did what are called as cognitive ethnographies. So these allow us to identify how is it that experts make sense of things, how is it that they do things, what are the cognitive processes underlying, and we really zoomed in on episodes, smaller episodes of what was happening. We had 2 experienced engineers who each solved 3 problems. We had videos and retrospective interviews with them, right? And I'll talk about the results next. So yeah, so what we did essentially was we looked at the process in its entirety. We tried to model it in terms of what is happening in its entirety. And then we also focused on certain moments of sort of breakthrough or discovery and tried to identify what was happening at that point, which can be productive for the estimation. So what we found was that model building and mental simulation were the drivers drivers of discovery, in the sense it's not any big discovery, but small discovery in this problem solving, and also that experts used created and used a lot of diagrams in their approach. What we found was that the first thing that experts did was they imagined, they modeled the dynamics of the system. So they imagined what is it that the system does, how does it behave, what are its moving parts, what goes where, and so on. And we found that this process was, the cognitive process supporting this was mental simulation, as we saw evidence in their gestures and their speech. And then they move slowly towards building relationships between the different parts, between the different parameters. So if they are thinking about, one of the problems we gave them was, what is the power of the heart? So they're trying to build a model of what does the heart look like, what does it do, what goes where, what are the parameters. Okay, so there is blood, and then the blood is flowing at a certain speed. How is that related with the blood pressure, the thickness of the valves, and so on? So that's how they are trying to make relationships. All of this time, they have not yet brought in any equation or anything like that. It's after they have these relationships sort of clear in their mind, then they bring in the equation and they say, okay, so this is how this is related, and these are the parameters I need to know, and this is how I'm going to solve the problem. What was very interesting was that throughout this was not some abstract thing which was done, without any meaning. The problem context was very central to the expert's reasoning throughout. So what is being asked in the problem was used very intricately in their problem solving.
They are bringing in equations or constructing equations?
They're So the question is, are they bringing in equation or are they constructing equations? So yes, they are constructing equations. On the basis of whatever parameters are involved, they are constructing equations.
By the way, we are just about past an hour.
Yeah.
And you'll finish this and then you'll also tell us a little bit about what we practice.
Yes, I'm going to not do this in great detail. I'll stop after some time. Yeah. So these first two steps are sort of this, problem space expansion. You're thinking in all directions, and then slowly towards the end, you are freezing it. Okay. What is important to note is that this internal speech is constantly running in an expert's mind. So what am I doing? Why am I doing this? Is this right? Does this fit? Does this make sense? This is constantly running, and this is what is guiding the expert from one model to the next, and then checking, and if it doesn't make sense, actually coming back. So this process is not a simple, 1-3 level process. It's a very intricate process with a lot of iterations and a lot of loops and a lot of going back and forth. So yeah, so the significant role of internal speech is one of the other important takeaways for us. So we did a similar thing with novices, except one of the things we also focused on in this was try to identify specifically what were the challenges that they were facing. So what was the pain points that they were having. And for this, we did another study as well, and 2 studies to kind of identify what were their challenges. Together, we were able to identify the expert-novice differences in estimation. And as Savita was asking yesterday, this is a very standard approach in problem solving to try and identify what are the differences between experts and novices, and then use that to build interventions. So in terms of overall approach, the experts have model-based estimation. Novices are just searching for an equation. The problem context is integrated throughout, whereas in the novices case, it's integrated at the end. The primary cognitive mechanism for experts is mental simulation. For novices, it's equation manipulation. Reflection, this is well known throughout literature that experts reflect, revise. Novices rarely do that. Information gathering was another one. When experts were searching for information about the problem system, and novices wanted to search for information about the right equation. So again, that perspective shift stays throughout. And the role of conceptual knowledge is also different. So this knowledge or information now feeds into our design. So and then we also found out some challenges which are there at the right. And so what we find is that these are the challenges that novices are having. We need to scaffold them to overcome these challenges, and we need to trigger certain productive actions that experts are taking. We are not saying that we want them to do this exact process, because even experts don't follow like an exact process. But there are certain productive actions like simulating the system, like considering the problem context, reflecting on their model. So we want them to do these actions, and that is what we try to focus on in the learning environment. So then on the basis of this, to where we go on, we ask what is a kind of learning environment that is needed. We make some conjectures about that. We use literature to guide us about what are the features that should be there in the learning environment. And then we built this learning environment, which I talked about yesterday already. I'm not going to repeat that. We had two versions of this. We evaluated each of these. Okay.
I think there is some disturbance. Maybe people can mute.
It's okay. I muted. Go ahead.
Okay. So then we identified, so we did the studies, and we identified some of the patterns of interaction of the students with the system. So we first characterized the performance. We had 2 high performers, 3 low performers, and 5 medium performers. And we tried to see what was it that each of these category of people were doing within the environment. So what we found was that so we can see this is basically talking about what was the sequence that they were following. And a green arrow means that that activity was done productively. And so what we see is that high performers actually focused a lot on this functional and the qualitative models. They used the evaluation prompts that were there. They reflected, evaluated, and so on. The medium performers, they did not use the prompts in a very productive way. They did not see the value. So they saw the prompts as questions. They did not see them as something that was going to help them solve the problem, but as a question that was just there. So what they were having more was a sort of a goal-driven approach. So how can I get to the answer? So you can see here the fact that they were going more towards they were going towards the calculation and then trying to see if it's correct, calculation and evaluation. If it's correct, then I'll finish it. If it's not, then I'll come back and see what else I should do. So it was more of a local sort of an approach. Whereas the low performers, they also interacted a lot with the system. In fact, they did interact a lot in the modeling phases. But what we found during the retrospective interviews was that their conceptual knowledge, which they needed, was so poor that they could not make sense of the material that was there in the environment, which sort of tells us that this we need to integrate these kinds of activities more coherently into the curriculum, so that students are doing more of these and they are learning more how to apply this concepts that they are learning in during their studies. So this was one way for us to identify whether each of the features that we had put in, whether they are working, they are not. So some of the features worked the way we wanted them. For example, the open-ended environment gives people the affordance to do the problem in any way that they want, but it's not enough, in the sense that students need more guidance. Like, for example, with the medium performers, we need to give them something more to convince them that why are they doing this evaluation? Why should they be thinking about these factors and so on? Okay, again, these are more like a summary of findings, but what implications these give us is that so students do need to focus more on this functional and qualitative modeling, and it requires sort of a mindset shift which has to come in more integrally into the curriculum, because the curriculum currently places so much value on closed problems, on equation solving, and so on. Students don't see the value of these practices such as mental simulation and drawing diagrams and building models and evaluating them and so on. So this is not something that can be done with one intervention. It needs to come in more systematically. And one of the suggestions that I have is to have estimation activities associated with most of the problem solving sessions that are there. So every problem solving session should have some estimation problem associated with it so that students do that. So what are there any questions? Maybe I just pause for questions and then move on.
Only question is that we should go on.
Mm-hmm. Okay. So what these two approaches give us is that, so the first approach is more data driven. It allows us to deal with large corpuses of data. It allows us to identify what are the action profiles of people, just on the basis of data. It allows us to see patterns which we cannot see. It allows real-time analysis. On the other hand, this ethnographic and interaction analysis gives us a way to analyze speech and action in context. It allows us to interpret the whole process, and the moments of breakthrough and so on. What we don't have with the quantitative approaches is, like I said, we don't have the qualitative approaches. Another problem is that it's only as good as the features that you select. And here, you have to use some knowledge of the task itself to be able to use the right kind of features. So for example, in our task, we know that it's the number of additions, deletions, looking at certain things and so on. So that analysis is only as good as the features that we select. On the other hand, the ethnographic analysis is difficult to make patterns, and it's not scalable with larger corpus of data. So what I propose to do with makerspaces, which are going, is to integrate these two approaches, and I'll talk about how I want to do that. So makerspaces are, we know, so they are places for innovation and creation, and they present an opportunity for learning, which is sort of complementary to classrooms and labs. And there is some literature in the West which suggests that students can learn many things from this, so including conceptual learning, right? So the questions that I want to ask is, what does learning in makerspaces look like? And how can we design to make this learning happen? So this is especially important right now because we have these Atal Tinkering Labs. Huge amounts of money is pouring into them. There are apparently 10,000 plus labs right now. There's a claim that there are some 75 lakh projects made, but there is no evaluation. We don't know how it's working. We don't know in what state these are. We don't know how many people are using them, whether this is even correct, what kind of numbers are these. So
50 lakh into 10,000.
Yeah, that's the money which has gone into it. And I'm presuming all the other expenses that go along with it. So given that so much money has already gone into it, it makes sense then to analyze this very systematically to understand what is it that they could be bringing. So I want to again bring a design-based research approach where we extend theory, like we said, we bring the 4E cognition models. We talk about what do they tell us about innovation learning. We have design principles, which we instantiate, we evaluate them, we analyze learning, and then we are able to contribute back to theory and come up with new design principles. So here we use cognitive and learning sciences, HCI, and a lot of methods which I described right now. So my proposal is that we begin from the evaluation part, which means we do, we start by looking at literature. We identify some conjectures related to the learning and the making process in 4E cognition. We do in the wild studies with people in current maker spaces, and we try to get a wide variety of people. Here, when I mean experts, there's it's just terminology. What I mean is people who are new to tinkering, people who have been tinkering for a while, and perhaps people who are in the middle. And then we will have to necessarily collect multimodal data because people will be working with objects. So we need to see what they are doing with their hands. We need to see where they are looking. If they are using a tool, we need to see what they are doing with the tool. If they're using their computer, we need to see what actions they are doing within the computer. So necessarily, there will be multimodal data. And we will have to do quantitative rich analysis. So again, I'm propose an activist approach to this. I say 4E cognition, but it's primarily an activist, where we are focusing on actions and doing. And we then try to relate this to conceptual learning and making performances. So the analysis approach that I propose is to combine, like I said, quantitative analysis and qualitative analysis. We do quantitative analysis purely as exploration to identify relationships, patterns, and trends which the human eye cannot see. But at the end, in order to build processes, we need to do qualitative analysis, which are hypothesis driven, which are interpretive, where we as researchers focus on the activity, and we try to zoom in into moments of breakthrough, identify what is happening, identify the interplay between the actions, and then build these models of process and learning. So one example analysis what I would do is, if there was a hypothesis that the prototypes that people build in the real world, and when they interact with them with mental simulation, but also with experimentation, that's going to change the understanding of the problem. So here we have to, in terms of qualitative analysis, we have to examine the nature of the prototypes, drawings, whatever they've created. If they've been speaking, then speaking and so on. But we have to look at their gestures. We have to look at whatever material that they have been using and so on, and try to identify if there's any evidence of mental simulation. Then we also can look at quantitative data, such as how many prototypes did they build, how many experiments did they run, where were they looking, transitions in eye gaze, how much time were they spending on each of these activities, how much were they speaking, and so on, and then try to identify to see if we can sort of, from these actions, we can build some profiles of learners and not. So what I expect to find is a model of the making and learning process. What will experts, let's say different levels of makers, let's not call them experts and so on, but different levels of makers, what do they do? What are their differences? What are the cognitive processes that drive breakthroughs? What are the productive actions that drive breakthroughs? How are these interplaying during breakthroughs? And this will then lead to redesign. So now we intervene at another point of the design-based research cycle. We know that, what are the productive actions, we know what are novice challenges, and then we know what kind of interplays we need to trigger. So then we use design principles from the relevant areas, and we intervene and redesign makerspaces. So that would be phase 2 of my proposal. So what I envision is that this is the resources that I think such a project would entail. The analysis part itself is one PhD student's work, and then redesigning these We would need software and hardware developers. We'd need a dedicated makerspace with some sort of prototyping tools, Arduinos, maybe for kids, even something like Lego Mindstorm, which is much easier and accessible, all the sensors, motors, and so on. The experimental setup would have to be like with eye trackers, video cameras, recorders, software, computers, so on. And these are the kind of collaborations that I also envision, both within HBCSE. I met a lot of people who are doing this actually, so I'm happy to collaborate with a lot of other people as well, just a few that mentioned, and also externally with people that I have been working with in the past, and I hope to continue working with on the multimodal data analytics part. And that's sort of the end of my talk.
Okay, I guess it's a question from.
Can I go if unless there's someone else, because I've already spoken quite a bit. Okay. So a couple of questions, Aditi. I'll say both and then you can answer them. One is that, in this situation in, say, India, also in Homi Bhabha Center, is somewhat different from the situation you're just coming from, in the sense that the teams are rather small. And so typically the PI will have to sort of get herself, get a lot of expertise, drive many different aspects. Here there is, for example, in the tinkering lab, designing of activities, making some kind of objects, designing tasks for students, putting together those materials, the equipment, etc. Doing some amount of software. So quite a bit of this, actually, the PI has to multitask, because there are not teams with the different expertises collaborating and so on. I mean, you can look for, I think Sanjay was pretty lucky in finding Harshit and people like that, and you can look for them, but it may not happen automatically. That's one thing. So, do you feel confident in launching fairly complex research projects of the type that you outline, given these constraints? That is my first question. And, would you like to comment on that? You can do that. The second question I have is that, your first study that you described today was very interesting to me, because it had a way of analyzing social interaction between two students and using purely behavioral measures and so on. And the part of the what was good about it was the nice task which was set up, and the task setting which allowed you to gather data which could then be meaningfully analyzed. Now, you spoke about the tinkering lab in general, but could you kind of sort of describe or sketch some such activity or task in the learning, in the makerspace environment, which will allow you to gather this kind of data? Or perhaps you've thought of it already, or maybe if you haven't, you can just generate some thing. And what are you thinking along those lines? That's my sort of my two questions. Yeah, thanks.
Yeah. So in terms of doing such a project, I am quite comfortable with doing the analysis, the multimodal analysis and everything by myself. Yes, I have not set up a makerspace, but I have done what are called studies in makerspaces. They were not part of my dissertation ultimately, but in the makerspace in IIT Bombay, for instance, I did go and do some field work, and I studied how people were working over there. I collected some data. So I am familiar with how to collect data in a setup makerspace, how we would, for example, set up things and how we would collect data, and then how we can analyze it later on, because the analysis is the combination of the two methods which I was talking about. So yes, setting up the makerspace would be a challenge. So that is where I am hoping for people with the expertise, and I, from what I've seen in the 2 days, there is a lot of expertise within HBCSE of people who know how to make things, who know how to fabricate, and I hope that I will be able to work with them and set up a makerspace. If not, my approach would be to try and go into makerspaces outside of HBCSE, which were already set up, so that the work doesn't stop. So that while we are trying to acquire the expertise, while we are trying to learn, we also keep continuing our work in the field by going to other makerspaces which are around in the area and trying to study the people. But I'm quite confident that we can find that the expertise exists. It's about finding the right people and building the bridges and finding it. Okay, so in terms of the task, you rightly said that the task which we had in the first study was very nicely designed. It had the switching and just using the behaviors we could study a lot. So within the makerspace, whenever we do these in the wild studies, the task is very important. So even when we studied with the experts and novices, we have to really find a task at the right level, so that we get authentic practices from both the experts and the novices. It should be a task which is challenging to them, yet something which they are able to approach. Because otherwise, if it's not challenging, then what we are seeing is just them doing some procedures which they have internalized. So we really need to find a challenge. So here, my guess is, from what I've been thinking about it, my guess is that we may need to have different levels of tasks for experts and novices. For novices, let's say if we're working with younger children, I would be inclined to give them something with a Lego Mindstorm, let's say program the Lego Mindstorm to maybe make a sweeper, attach something to it to make a sweeper. So it has to go between two lines, and it has to sweep all the kachra which is there between these two lines. So this is one kind of activity that could be done with kids, because they like Lego Mindstorms, for example. With slightly older students, maybe college students, we could do some activity with making them make some kind of a little lamp or a sort of a light kind of structure with LEDs or something like that. When they have not yet done too much if they are engineers, then they have not yet done too much in their engineers, but basic things where they have to build some kind of a simple sensor actuator kind of task. For people who have been making for a while, that kind of task has to really be designed. It cannot be something this simple, but it has to be something with multiple challenges, somewhere where there is some breakthrough, and that's something that will require more thought. To maybe it requires a few observations first, and that's something that also we did a lot of, I did a lot for the expert studies with the estimation, is to go and just watch experts to see the kind of work they were doing and then formulate a task. So that's something that I may do again. Yeah.
Thanks.
Does that answer your questions, Ravi?
Yes. Yeah, very well. Thanks.
Okay, Aniket, you have your hand raised. Go ahead.
Yeah, sorry. Since Aditi, you were mentioning about Lego Mindstorms. If you go to market and see the cost of even the most
Aniket, we can't hear you.
Yeah, cannot hear him.
Aniket, are you there? Aniket, you're muted, at least according to the display here. Can you hear us? Okay, he will type his question. Meanwhile, Jaykumar, why don't you go ahead?
Hi. So I had some questions about the spanning tree experiment that you described. Yeah? Hello, can you hear me?
I didn't hear the last part of what you said. Which experiment?
I mean, the example using spanning trees.
Spanning
construction.
trees. Yeah.
Now, so there are these two agents, two people who are playing the game, sort of, and one of them has a realistic looking map and the other has an abstraction, right?
Yeah.
So now, in the abstraction, are the relative positions of the various locations maintained, or they are jumbled up?
No, they are maintained, I believe.
So in that case, it is not really an abstraction, right? You have just removed the distractions of those trees and bridges and
yes.
Mountains.
Yes.
But otherwise, it is it's not a full abstraction in the sense of a graph being an abstraction of a road network.
No, you're right. No, it's not like that. It was just meant to be by removing the distraction. Yes.
I see. Okay. Now, so suppose they have, I just want to understand in what sense this whole thing is a learning experiment. So suppose we give them one such map and the two agents play with it and eventually they figure out or they come to an agreement as to what the right way of connecting these things up is. And then we take this map away and give them a new map. Will they now be faster than they were before? Have they learned anything? Isn't that the experiment that we should do?
That actually what we did was we had pre and post tests where they had questions like this. So they had 10 questions where we asked them to, there were questions about spanning trees. So for different kinds of small maps, so which one is reducible, which one is fully connected. I mean, not in those terms, but in terms for kids. So in which one is there a path where you can go by walking on fewer stones, things like that. So there were a bunch of questions that were asked to them before and later, and that's how we measured the learning. So in what you're saying is correct. There were these kind of questions. They were given another map, but on paper. They were not doing it, not on paper, sorry, in the system, but without the interaction. They just had to think about it and answer the questions.
I see.
So they had 10 questions in the pre and the 10 questions in the post test.
Yeah. So my next question is not about this learning itself, but yesterday you mentioned the use of a greedy approach. Yeah. That is, there is a greedy approach to solving this problem. Yeah. And but I mean, so I'm somewhat familiar with spanning trees. So there are several approaches to solving the spanning tree problem. All of them can be called greedy approaches in one way or the other. So is there a sense of which one of those approaches they seem to arrive at rather than the other approach? I'm just saying that in computer science literature, there is something called the Dijkstra algorithm. There is something called the Kruskal algorithm. And there is supposed to be something from the early 1990s called the Burovka algorithm. And all of them are greedy in one way or the other. So was there, I mean, some sense of which algorithm students considered natural enough that they could themselves arrive at?
No, we did not do that analysis actually.
Okay.
But that's a nice analysis that we could potentially do, but we did not actually do that.
But in the end, after they have learned, if you ask them like what are they able to articulate a notion of an algorithm? That is, suppose they were to explain to someone else what building a spanning tree is. So after all, we are talking about learning algorithms, and in the end, the algorithms will have to be written down. So will they be able to articulate what they did?
That's a good point. We didn't investigate that, and that is a limitation of this study, because the questions were entirely like multiple choice questions on what you would do. We did not actually explore what they learned in a more qualitative sense, and that's a limitation. So that's a limitation of the study. Yeah, that's all I can say. But it's important. What you're saying is important. They do need to get that notion of the algorithm, but we didn't measure it.
Vandana, you were saying something, or can I ask one more?
Go ahead.
Yeah, no. So this is not related to spanning trees anymore. You mentioned Markov processes. Yes. So usually Markov processes are things where when you are at a particular state, you don't have memory of the previous states. But I would think that a learning process, usually like memory is a very important thing. And that is what we are basically trying to instill through learning. So how fair is it to call something Markov?
It's a Markov model. So what? Yeah. So yeah, you're right. And I have thought about it. It's probably not fair, because even in terms of actions, we are only doing the Markov modeling on the actions, but I'm pretty sure there is some memory on the actions as well. And we are sort of compartmentalizing the actions. What helps is we are compartmentalizing the actions into 10-second windows. But still, you're right, probably one 10-second window is not related only to its previous, but somehow the actions that they have done previously have built up. So maybe technically that assumption is not valid. But this gives us one way, the assumption gives us one way to look at it. And maybe the memory, there is some memory which is for a few previous windows, but it's not entire. That's hard to say. So yeah, it's not technically, the assumption is not technically valid, but we did not prove it, we did not check it, but we did assume it. Yes.
Thank you.
Can I ask, because I just have a follow-up question on Jaykumar's question.
Go ahead, Vandana, go ahead.
Yeah, so going back to his previous question, where we talked about that how people have learned in terms of the graph, and then you try to give them a different thing and see an effect. So you said you have not done that. But supposing now that this discussion has led you to also think that as one parameter, how would you think you can conduct this exercise, or how you can, what kind of test you would like to build into that? Can you elaborate on it?
Yeah. So what I would do over there is give them an alternate map and ask them to write how they would tell somebody else to connect the map. So essentially, as if they were explaining to a friend. Now, suppose if you have to explain to a friend how you would connect this map, what would you do? And so maybe get them to write out that algorithm, or maybe verbalize it if interviews, either way, and then analyze it.
Yes, sorry, the question is, I think the question which I also was trying to get to essentially through that is, okay, the map may not be same, right? The map may have evolved. So how do you introduce them to get to the concept of generating algorithm?
Okay, so this is where, so the idea of doing these activities is that they get some understanding of the notions of the algorithm and so on. What we envision always when we do these kind of activities is that after such an activity, there is a phase of debriefing by a teacher who then brings in these formal notions to them. So this is a model in pedagogy called as problem solving followed by instruction. So the idea is that this problem solving, grappling with the problem, makes them ready and aware of the concepts that are, or the notions that are involved, and then a teacher intervenes and gives them the formal notion. So that's how we envision this. There can never be an activity just purely where they are doing this. There has to be an intervention by a teacher for formalizing certain concepts.
Even if I grant that, the teachers may also need some orientation. So I guess what I'm trying to look at is do you have any suggestions or ideas on explaining these concepts of algorithm? Because you may also be, say, training teachers to do that or something like that.
No, we don't actually train teachers to do that. So these are investigated as standalone activities. And then
I have a slight problem, right? Then there is a slight problem. You have a certain activity on which you want to judge or assess something, and the part of the assessment is some inputs by the teacher, be it a debriefing or be it training, but then those are not involved. Or am I missing something?
No. So what I mean is, when we assess them, we don't assess them upon we assess them on the concepts that they have interacted with in the interface, those concepts at an intuitive level. If we want to make the concepts at an abstract level, like what is an algorithm, how does this algorithm work, and can you describe it to somebody else, that requires an additional intervention. The pre-test and the post-test is pitched at the level at which this intervention is designed. What I'm saying is that for somebody to learn this concept at the level at which you are suggesting, alone this intervention is not enough. So then we have to have the teachers who comes in and completes it according to their learning goals.
I agree, and anyway, I should also perhaps move on and we can discuss this later. But precisely the point was that you have described what you have done, but suppose it was to be extended, then you have to bring in intervention. What would you think about then? In what ways this intervention or then that training or that module will come in? Maybe you can think about it and we can discuss later.
Okay. Yeah, sure.
Okay, so let me take these questions from the. I'll start. Gian, I'll take yours later. Let me just finish Aniket's. He had started this. So this question is.
We can't hear you very clearly.
Can you hear me now?
Yeah, a little better.
Can you hear me?
Yeah, a little better.
Okay. Since you are talking about Lego Mindstorms, do you think that even most basic Lego mechanical sets are affordable for 95% of Indian schools? Apart from the financial aspect, do you think it is a good learning strategy to use LEDs, etc., like a black box? Wait, like a black. Just let me expand the chat.
Like a black box without first learning what LED is.
Without first learning what LED is. Inserting a diode in the circuit as per given diagram while having no idea how a diode works, does that really help students?
So about the cost aspect, I mentioned the Lego Mindstorm as a possible activity for doing studies, because it's something that in some work, in some small work that I have seen in previous workplace, it was very engaging to students, and it has a lot of affordances because of which they can build a lot of things. So it's engaging to students. So it's something, I don't envision that there will be one Lego Mindstorm in every school, but in a maker space, in a starting maker space, if you want to give them a task which engages them, one Mindstorm and having them work on it is what I was envisioning. Now, whether it is useful to to use LEDs and all without knowing how LEDs work, that really depends upon the goals of the activity. So if your goal is conceptually learning about how the LED works, then surely you should know about how it works before you do any kind of making activity. But in the maker space, or often when we do projects, sometimes there are things that we don't know how they work, but we learn how to use them in the process of doing. And that is one of the processes, conjectured processes of learning within maker spaces, where they learn on the go. So maybe by doing the process and then by experimenting, they can learn, they can build their conceptual understanding about these concepts.
Okay, question from GM. What can the makerspace without computers look like? Why there is the trend nowadays that every makerspace must have a computer interface? What about working and making with alternative materials and mechanics?
Yeah, I don't think that the makerspace has to have a computer, but we can have a makerspace is more about the processes than about the materials that we have. So it really, I mean, I'm not suggesting that we have the most advanced tools to do a makerspace, but there has to be some basic set of tools which they can do something. And what I would try to do is actually that. I mean, I have seen that yes, makerspaces have laser cutters and 3D printers and so on, but I would try to see what is something interesting that can be done with the minimal tools. I mean, you don't need computers all the time, but I mean, Lego Mindstorms was one specific thing because it's engaging to kids, but there can always be alternate tasks which can be low cost and simpler and so on. Yeah.
Okay, question from Sudhara. Can you please elaborate what are the educational benefits of makerspaces? Do they have any value in classroom learning besides hands-on experiences?
So, yeah, there was a, so there is a list of possible benefits and I'm just going to flash it, okay? But the idea is that this is preliminary research on what are the kinds of things that people can learn in makerspaces, right? There is some evidence of conceptual learning, some evidence of all of these kinds of, you know, what are now called 21st century skills. So creativity, risk-taking, fostering STEM identity, iterative prototyping, a lot of these things. What I am what I think is interesting about the makerspace and why I want to look at it is that these are spaces where people build things, they build physical things, and they, in the process, they have some moments of breakthrough, they learn, something happens, right? And we want to understand this process of, we want to understand the process of learning. If we want to change science education, we want to understand this process of learning. So given that we know that the recent cognitive theories tell us that learning is embodied, enactive, extended, embedded, we need to study it in such a way, in a context which allows for the embodiment, the enactiveness, all of this to show. And maker spaces are a good test bed where we can study this. So maker spaces gives us the opportunity to elicit those making and learning processes, which we can then study in detail and then redesign them and see whether they are working. Maybe nothing is happening, but it's one place where we can sort of bring those learning processes out, because now we know that the learning processes are based on action. It's when people do something that they learn. So we need to study it in its authentic scenario when people are doing something. And so I see the makerspaces as an ideal test bed to bring out those learning processes in an authentic scenario and then study them in a systematic manner. So that is the goal.
Vandana, your hand is still up. You have some more questions?
Yeah, just one question about the work which you want to do here.
Yes.
Can you go back to that slides, the projects which you have sort of projected? Towards the end.
Okay. This one.
Yeah, so in the so there are a few things here. What would be your top priority? What will be your, say, kind of the major thing?
First, yeah. Okay, my top priority is to do authentic studies in makerspaces, right? So for that, what we need is just the equipment. We just need video cameras, audio recorders, and eye trackers. And this can be done because even if we don't have a makerspace here, we can go to makerspaces in the field and study the, try co-design with the people over there, relevant tasks, and go and study over there. So this is my top priority. And I think this is immediately doable, even without having set up a makerspace. This is doable immediately, and that will be my top priority.
No, feasibility is one aspect, that is all right. But what I'm trying to get at is the significance of the project in the wider sense. Okay, in terms of the wider application to the overall science education program or this one. So from that point of view, can you elaborate a little bit?
Yeah. So let me go back then to this idea that the way that we can redesign science education is through this design-based research approach, where we try to study learning in its authentic form as it happens. And then we try to evaluate when is it that learning happens. And then that extends our understanding of learning itself. And on the basis of that, we can redesign, we get some design principles, and we can redesign learning environments of science education, right? So it all starts at this point, which is let's understand learning in its authentic context. We don't understand exactly how learning is happening, and that is the implication of doing this work first.
Okay, fine, thank you.
What do you mean by going to makerspace out there? Do you mean that thousand developing the labs, or when you say like
so that's what I'm trying to find out. And like what are in our vicinity or wherever, of course I know that engineering institutes have makerspaces and I would have access to that, but that is not desirable because then that limits us to older students. We want to also study younger students. So the goal would be to look for makerspaces, public makerspaces, either the adult tinkering labs, or nowadays I hear some schools have makerspaces. Try to go to those places and then work with the local people and try to design a task and work and study them as they are working.
Okay.
So Aditi, this is can I? Yeah. So Aditi, since you have been coming to HBCSE, I'm a bit curious to know whether you have seen, we have an area called design and technology. Have you seen the activities, any of the activities, If so, then I just would like to understand the approach which you are proposing and, this area, design and technology. How do they differ? Are they similar? Are they different? Or what is that you do differently, which is not explored as a part of design and technology?
So, I have visited the design and technology lab. So what is being done is there are some really cool activities to give people the design thinking skills. So creativity, decision making, thinking from the user's perspective. So students learn all of these skills. In my mind, it stops one step short of the process that I am proposing, which is that students should, after doing the design, they do some kind of prototyping. And I know there are some activities where they are doing prototypes as well. So it's not entirely something new that I'm proposing, but it's a little bit of an extension of what's in the D&T lab. So you have to do actively, the students have to participate in this prototyping, iterative prototyping process. So prototyping, experimentation, and so on, so that we can see these moments, where they notice their mistakes, where they find some breakthrough, where they learn something new. This process has to be made explicit. So I would say that these activities can be used, they just need to be elaborated to make it like more. It's not like a workshop where they are learning something, but there should be an element also of them doing it on their own and struggling with it a little bit and learning something new. So these activities can also be involved. They have to be extended a little bit to incorporate this.
But I think in those activities also there is a stage of reflection. There is a construction, and when they construct something, there is a lot. What I have seen, I've not seen everything, but what I have seen is that there is a stage of reflection where they really, comment upon. I think it's a process part of it actually.
No, for sure. What I'm saying is that the stage of reflection is there. What I'm saying is that they need to sort of complete this process by coming up with an improved prototype. So on the basis of that reflection, they need to go back and improve the prototypes and so on. So this process, it has to be a little bit longer is what I'm saying. So it's not just that after the reflection it ends. They need to go through this the iterations and learn about this process. That's all I'm proposing.
There's a question by GN. There is a question by GN. Can you read the chat? You can't read the chat.
Yes. GN's question is, what is your take on the distinction between learning skills and conceptual knowledge?
That's a very debated topic within science education as well. Are they separate? Is one based on the other, and so on? From what I have seen, learning skills like science process skills or problem solving, design, and so on, to some extent it's based on conceptual knowledge. It's based on under whatever understanding we have of the concepts which are involved underneath. And at least in estimation, which is also a skill, I saw that, because without having the conceptual knowledge, you can go only so far. At some point, the models will not be viable because they don't understand the conceptual knowledge. I do not believe that you can just transfer skills in abstraction. I believe that skills are very much connected to the conceptual knowledge, and maybe there's near transfer possible.
GN, you have your hand up.
Yeah, I mean, basically wanted to clarify the clarification that I wanted to seek, because from yesterday's presentation as well as from today's presentation, you have, theoretically and maybe philosophically oriented towards 4E cognition. And then in today, you have mentioned a lot about being an active and behavioristic kind of a model. And therefore, I'm motivated to ask this question actually, in the sense that, if you actually hold that kind of an active cognitive philosophy, okay, what happens to this distinction between conceptual knowledge and, skill-based knowledge? And where does it go? I want your response from that perspective. I mean, I know that it is a debated issue, and that's why I asked you, what's your take on that?
So, can I just ask what exactly you mean by skill? Is it the way that I was talking about it, science process skills and design and so on?
Well, essentially, see, if you look at, for example, India's Planning Commission, for example, has what is called a Commission for Skills. As if that is because the general understanding has been that the traditional conceptual and problem solving education that happens in the school and colleges is somehow neglected something else, which is called the skills. and that's a big, actually speaking, I mean, the maker spaces and things like that are also made part of that agenda,
Yeah.
and therefore, I want you to understand from an educational perspective, and also having adopted an activist cognitive perspective, how does this distinction actually sound? Do you really have to maintain this distinction, or do you question this distinction and then carry on with an active model?
So, I mean, the enactivist approach, the enactivist philosophy would suggest that both knowledge and skills are based on actions, right? And okay, so when I was talking about the skills being based on knowledge, I was talking about the experimentation and so on. I think that the skills which are being referred to in the framework you're talking about is probably more are there psychomotor skills by any chance?
Yeah, they're also part of the psychomotor skills, but then psychomotor skills are part of the enactive model as well, right?
Yes, yes. So I think the enactivist model would suggest that both of these are based, of course, on the actions, and yes, it would be hard to distinguish whether they can be separated or not, maybe that's something that I will have to reflect on further. So
okay, thanks. Yeah, that's fine. Yeah.
So I think maybe we can. Yeah.
I don't see any more questions on the chat or any more.
Yeah. So Rajesh, that's what I was saying, that maybe we can close the meeting now by thanking Aditi for her time and her talk. Yeah, okay. Can you do that?
So let's thank Aditi. The ones in the room will clap, the others can clap virtually.
Thank you.
Yeah, thank you. It's been really long. Yeah, thank you.
Thank you for having me.